Hello everyone, and welcome back to Python Testing with Pytest Motivation, Demonstration and Practices. This is part 2, where we're going to dive in with some real kind of code examples and demonstrations of Pytest. All of the code examples I'm showing in this video are available on GitHub. I will place a link in the video description. So, first scenario. Having motivated testing, let's show what it kind of looks like in terms of Pytest and what features we get out of the box. So this is our really complicated simulation library. I'm going to assume that you're somewhat familiar with Python, but I'm going to explain how the code works and roughly what it does. So on the left side of the screen we have my editor here. On the right we have a shell, which I can type commands in, as is fairly standard. So we have two functions. We have the function greater than 0, which returns true if the number we pass it is greater than 0, and returns false if it's not. And we have a test function. We have test greater than 0, which has 4 tests inside of it, which tests whether or not certain numbers are greater than 0 or not. So let's just get stuck right in, I suppose. So Pytest can be invoked from the command line by typing Pytest and the name of the file you want to scan for tests, like this. We run it by pressing return and we get a lot of output. So let me talk a little bit about what we've got here. So at the start we have some preamble here where we're talking about what system we're running on. You can see my file system as well and some plugins we have. We see that Pytest has collected an item, so it's found a test, and that test is in trivialmathematics.py, and the test has failed. That's what the F shows you. Now this output here is all very useful. It shows us what function has failed, test greater than 0. It shows us the line that has caused it to fail, and it has shown us that it's found that greater than 0, 0 is actually true and is not false. So that's why the tests are reporting that the software has failed. So we can fix this. I mean, the simulation library is broken because this greater than or equal to 0 should really just be a greater than 0. So if we save that file and wrap that, we can run the tests again and see what output we get. So in this case, the output is very similar. We have again collected one item. We've collected trivialmathematics.py, and that test has passed. That's what the dot means. And we see 1 passed in the kind of output at the end, just to make it even more clear. Now if you want a bit more information, you can run Pytest with the verbose flag. And this gives us more information about what test has actually run. It's told us that test greater than 0 has run, and that it's passed, and that there's not a dot here. As we'll see later, the verbose flag does give us a lot more information in a more detailed context than we need here. So this is the first example I have. It's shown us that you can test code with Pytest, and that Pytest tells you what tests fail, and it tells you a little bit about those failed tests as well with its informative output. Now the interesting thing about this is somehow, some way, Pytest searches for your tests for you. We didn't tell it to run the function test greater than 0 at all here. Pytest just knew that that was what we wanted to call. Now that could be kind of a bit scary, a bit intimidating. So I want to talk a little bit about how Pytest actually, well, on a very high level, works. There are 2 core stages to the execution of Pytest. There's test collection, which imports the test file, which is here trivialmathematics.py. So it's a Python import, and it scans in that file for functions and classes with the word test in the handle. So we can see that our first function, greater than 0, doesn't have the word test in the handle, whereas the second function does, so it gets collected. On execution, the functions get called by Pytest, and there is some introspection going on in order to determine where things fail and why things fail. I've also written here calls, dependencies, and fixtures, and that's what I'm going on into the next scenario. So I think that's fairly clear. The second scenario we have is a simple data processing library. So let's say you have a temperature sensor, and that temperature sensor, when it reads temperature data, it gives you an integer back. This is fairly typical of hardware. But in order for us to understand what the temperature is and whether or not the sensor has an internal error, we typically need to convert this data into a binary format and interpret each bit individually of the others. So this is going to be a very simple example that takes an integer and converts it into a binary. So we have 3 functions here. We have our convert integer to binary function that takes an integer and converts it into a binary string. And it also zero pads the returned string. So typically what you want when you're parsing this kind of data is you would return a certain number of bytes of data, and so you want to make sure that the data that's not returned is zeroed. We also have 2 test functions here. We have test my converter and test even more. Now this is not good convention. In fact, you shouldn't define your tests as we did in the first example. You shouldn't define your tests in one single function here, but I'm going to come onto that in the next scenario. So what happens when we run Pytest on this? Let's see. Well, I'm going to move the output slightly just to make it slightly more legible. Here we are. So we can see that 2 items have been collected, 1 test has passed and 1 test has failed. We know that of those tests, test even more has failed because we can see that this number is what 191 is in binary, but we've actually said in this line here that it's 1, 2, 3, 4, 5, 6, 7, 8 ones, which it isn't, and that's wrong. So in this case, the test is wrong and not the software, so we should amend our test to fix it. We can also see some other interesting things about this error. Because Pytest here is comparing strings, we can see that it's actually tried to conduct a diff to understand what exactly is different. And that's a nice little user convenience that I appreciate with Pytest. So we replace our rogue 1 with a 0, and we run our tests again. And we see that the 2 tests pass. I think that's fairly straightforward. Now there was something a bit more sinister with this failing example. I'm just going to put the code back to demonstrate it. In test even more, we have a failure on the first line of code. In this case, the second test here has not even run. And that's very dangerous because when we want our test suite to run, we typically don't want it to exit on the first failure. Pytest can be configured to do that externally, as a command line flag, but this is not typically what we want. We want it to run through all our tests so we get the most information possible so we can debug the output better. So to summarize that example, automatic test collection is useful. Because we've managed to collect 2 tests now, if we wanted to specify tests by hand, you could see how this could become excessive with many, many tests. Pytest has shown us in detail why our assertion failed, because it gave us a string diff, but this example has highlighted that we need to be able to parameterize tests, because if we can parameterize tests and have them run individually, we won't have this problem of tests blocking other tests from running, and that's certainly not ideal. So now I'm going to move on to scenario 3, where we look at a way of parameterizing tests using Pytest, using the same data processing library example. So here is my code. You can see that I've made a few changes here. The integer to binary function is only one, it's still the same as it was, but we only have one test function, and I have changed the test to include a dictionary. So this test case dictionary puts the input into integer to binary, and it compares the resulting output with the expected result in the dictionary. In this way, this test case dictionary completely defines our test. So it's a fairly simple transformation. We can run the test again by way of demonstration that it still works, and it does. But this is not useful in and of itself because we're only running one test here. What we really want to do is run many tests. But before we get to the many tests, I'm going to introduce fixtures. Fixture. There we go. So now we have three windows open. We have this top window here, where we have the single example I've just run the tests on. We have this bottom window here, where we have refactored our test. And, well, I think this is simpler, in my opinion. I'm actually going to, yes, we have two functions here. I'm going to hide this simple example. We have our integer to binary function, again unchanged, and we have a test case fixture here, marked by the decorator pytest.fixture, that returns this dictionary. And we've changed our test function to include this argument, which matches the name of our fixture. And this result and assert is the same as the previous example where we only had one case. So a fixture is a piece of code that's run when a test needs it to be run, in the general case. In this way, we can say, okay, I want to test my converter. I'm going to collect tests. I'm going to run my test my converter test. But Pytest sees that there is a fixture here. It sees the fixture test case. So it executes the fixture test case and puts the return value in here, binding it to the test case variable. So that's interesting. Let's see if it works. And it does indeed work. So test my converter has encouraged Pytest to call test case. The dictionary has been returned, and the input has been passed to integer to binary, which has returned the correct value, which test my converter has confirmed. Now again, this is not useful in and of itself, because we're still running only one test, and if anything, we have kind of increased the code complexity by adding this extra function. So now I'm going to explain how we can parameterize tests using fixtures. So this script is exactly the same, apart from the fact that we have more of these kind of parameters in here. We've moved our dictionary into this parameters keyword of the fixture, and we now return this. So request is a Pytest object, or Pytest in origin object, and Pytest.request.param literally returns the parameter that the fixture is called with. Pytest will call this fixture once for each parameter, and we have 3 parameters, because we have 3 inputs and 3 expected results. So wherever this fixture is used, Pytest will actually call the test that uses it 3 times, or as many times as there are parameters. So let's run these tests and see what happens. We have a failure, but we have collected 3 items. We have the first one passes, the second one fails, and the third one also passes. Note that the third test has still run, even though the second test has failed. It has not prevented the third test from running in any way. And we can see here that it's very simple in its failure. We've got the result 101 from our integer to binary function, which is of course the binary version of 5. Our expected result is 0, which is not 5 in binary, it's 0. So the test is wrong, and we should fix it. If I run this again, the tests all pass, and that's great. You can see from this result that we have very little code duplication here. We only have our parameter sets expressed in the fixture params keyword argument, and that's a very elegant way of organizing your parameters and your fixtures. Tests can have any number of fixtures. As far as I'm aware, there's no hard upper limit, so you can also kind of do a matrix parameterization if you're so inclined. Now, the last thing I want to show before leaving this example is the verbose output when using fixtures. In fact, I'm going to move this shell along a bit and run that again. Yeah. So we can see the 3 tests that have run. They actually show you, Pytest will show you which parameter of the fixture is called by this test. So we can see that test case 0 has passed, 1 has passed, and 2 has passed. This allows us to more easily identify which parameter set has broken or has failed in testing. And there are ways of renaming these fixture outputs inside these square brackets, but I'm not coming on to that in this talk. So let me summarize scenario 3. Fixtures are kind of blocks of functionality that allow us to split up tests into smaller sections and allow us to easily parameterize tests as well. Fixtures are run when needed and when appropriate. There is a bit more fine-grained control that the developer has over when fixtures are run, but I'm again not covering that here. Now, there is a simpler way of doing parameterization. You can use the Pytest mark parameterise decorator to use it. However, I personally have found that this fixture way of doing things is a lot more elegant when you have to modify your parameters in here, or when you have to do some setup or teardown. I personally find this more elegant, but the syntax is very similar, so depending on your use case, you may prefer Pytest mark parameterise. You add the decorator to the top of your test, and the test will run in a similar way. So thank you for joining me on this journey of these 3 code scenarios where I've introduced Pytest, I've talked about fixtures, I've talked about the output of Pytest being useful for failure diagnosis, and parameterizing tests. In the third and final part of this video series, I'm going to talk through 2 more scenarios, and I'm going to wrap up the talk with some quick-fire useful things that I've found in my however many years of practicing Python. Thank you very much for watching this video, and I hope you'll join me for the third and final part.